Yay. Okay. So hello everyone. Good to well, I'm not seeing you. I guess you're seeing me right now, but still good to know that everyone is seeing me. So I guess today what I will be talking about is some kind of general things to do with ETH2 and uh, basically a kind of understanding ETH2 in terms of kind of the history and of where ETH2 started from, and some of the challenges and kind of some of the, I guess, steps that the Ethereum 2 and proof of stake and scaling, I guess, roadmap and movement has taken along the way. So first of all, happy birthday, Ethereum. Ethereum is, as of July 30th, 5 years old. So yay. And this cake picture I found on the internet just happens to have 5 candles on it, so that made my photoshopping, or rather a kind of gimping job, very easy. So yay, 5 candles for 5 years. Ethereum's 5 years old now. So moving on. ETH2, right? Or Ethereum 2.0, or Serenity, or there's kind of a lot of names for it. There's kind of two main goals for ETH2. So first of all, there is more secure and efficient kind of consensus through proof of stake. So I talk about proof of stake a lot. I talk about the need to replace proof of work with something more efficient. There's a FAQ. If you just search proof of stake FAQ, you can find it, that goes through all of my reasons for why proof of stake is great, and proof of stake is the future of crypto. Sharding is the other major goal, and sharding enables much higher scalability by moving away from every node needing to verify every transaction. And there's a bunch of other incidental improvements along the way, right? So I have a bunch of kind of small examples. SSZ, so replacing kind of RLP with a simple serialize, which is just simpler and more efficient. Binary trees instead of hex trees, stateless client verification, better light client support, and there's a long list of kind of lessons that we've learned from ETH1 that are kind of interesting by themselves, but they tend to be fairly small and technical, so I'll kind of skip past them and just say, no, there's a lot of things that we learned, and ETH2 is trying really hard to make all of those things better. But you probably know all this, right? But so let's kind of go back and look at the history of ETH2. So proof of stake in Ethereum started with this blog post I have on the right, screenshotted, which proposes a slasher, a punitive proof of stake algorithm. And slasher is interesting because it's the first, I believe, proof of stake proposal that seriously takes into consideration this idea that we should look for and penalize misbehavior, right? So we should actually look out for the possibility that validators would misbehave, say by signing two conflicting blocks, and we should just make that not be a good strategy by just explicitly adding a penalty for it. So this was done in response to one of the main criticisms of proof of stake, which is this idea called nothing at stake, which is basically that if a proof of stake chain without penalties kind of splits and there's two competing chains, then it's in everyone's interest to just support both of the chains so they can get rewards on either side, no matter which side wins. But if everyone does that, then everyone just keeps voting on both chains, and then if there's more chains, everyone keeps voting on even more chains, and so the system never kind of ends up converging on one, even if there's no attacker. So adding penalties, Slasher kind of fixes this, though Slasher does have some problems, and it's definitely not the sort of there's a risk of it getting stuck, and there's a bunch of other issues, but it did kind of introduce that really core concept, right? This concept of what we call slashing, this idea that if you get caught and kind of doing some provably malicious action, then you can be penalized as part of the protocol. November 2014, I released a blog post on the Ethereum blog where I introduced the notion of weak subjectivity, right? So this is the security model of proof of stake that basically says that kind of clients have to log on and go online like once every some period of time. So like, for example, once every 4 months. And the idea here basically is that like nothing at stake relies on this idea that we can penalize misbehavior. But in order to penalize, you have to have there has to have to be coins that are locked into the system that the penalty can be taken away from, right? Because once those coins are not locked, then whoever is supposed to get those coins can take them out and move them somewhere else, and the protocol has no way to penalize you anymore. I mean, and so the question is kind of how long do you keep those coins locked? And to prevent attacks where an attacker tries to start a chain that's an even older one than when those coins got locked, basically what happens is that you just require the client to log on once in a while, and a chain that basically if a client sees a chain, then another chain that tries to revert too many blocks back in history is just illegal. Like a client just doesn't accept it, right? So this also applies in the context of 51% attacks. So, for example, in a situation similar to, like, say, where ETC got attacked and there were 51% attacks about a week ago, in a proof of stake system, what would happen is that we would just kind of coordinate around not accepting the attacker chain. And furthermore, the algorithms can be designed in such a way that anyone who participated in the attacker chain just gets slashed. 2015, a first sharding paper released. So few have actually heard of this paper. It's sitting in GitHub. It's, I think, GitHub slash vbuterin slash scalability paper dash paper underscore paper, one of those two. You can find it if you just like do some archaeology digging through my repos. But the paper is like fairly long. It does some math around quadratic sharding, super quadratic sharding, committees, hypercube designs, a lot of interesting things. So 2015 was also around the time when we started kind of really going deeper and trying to come up with better proof of stake algorithms. So in 2014, we were kind of not certain whether or not proof of stake is really viable or a thing. But by the end of 2014, we're basically kind of certain, proof of stake is extremely theoretically sound, and we're going forward with it. 2016, a lot of research of traditional BFT theory. 2017, at the beginning of the year, I released this post called Minimal Slashing Conditions, which then got refined a bit and turned into the Casper FFG paper, right? So this is this thing at the it's from myself and Virgil. And what basically the idea behind Casper FFG is to try to kind of combine together the benefits of what I call chain-based proof of stake, or kind of Nakamoto-style proof of stake, where you just have blocks coming in one at a time and it's a chain, with traditional BFT consensus. So things like PBFT, Tendermint, basically things that have some kind of 2/3 rule in them. I mean, they don't technically have to have a 2/3 rule, but they usually do. So, proof of stake design philosophy, right? Probably the most important thing in proof of stake design philosophy is this idea that attack must be cheaper than defense. So in proof of work, like there's this kind of inherent symmetry, right? Attack is as expensive as defense. If it takes $100,000 for the good guys to make some sequence of blocks, it takes $100,001 for the attacker to make a longer series of blocks and fork that chain away. So chains are only as difficult to destroy as they are to create, which puts a serious cap on proof of work chains security. And I, in this post, even argue that that kind of one-to-one attack defense relationship basically violates the cypherpunk ethos, right? The cypherpunk ethos is fundamentally about this idea that on the internet we can make defense be much cheaper than attack, and cryptography accomplishes this, and proof of work does not accomplish this, but proof of stake can, especially if you use penalties. Also talk about how an occasional reliance on social consensus is okay. So like weak subjectivity is an example, recovery from 51% attacks is an example. So if a 51% attack happens, you don't just have to kind of sit back and accept it and accept the attacker's chain as being legitimate. You can kind of, as a community, say, well, no, screw you, we're not accepting your chain, and now your coins are burned, and muhaha, you can't attack us again. Which is definitely looking like a better and better security strategy, especially in light of systems like ETC, for example, just being 51% attacked over and over again. Relying on economic incentives for security. So basically, like the idea is that these are open systems, and in an open system, you can't like if someone does something like first of all, you can't know that people won't do something bad because you know them as a person. You can't know that people won't do something bad because some government will go after them because they might be anonymous, which makes it really hard for governments to go after them. So instead of trying to rely on a kind of trust-based and a very person-specific incentives, we just rely on economic incentives, rewards, penalties. The ideal goal is to make it impossible to do a 51% attack without losing millions of ETH to that ETH being slashed or to that ETH being lost in an activity leak. So we have a proof of stake based on a Casper FFG plus LMD Ghost. As I mentioned, combines together the benefits of a traditional BFT consensus and a chain-based consensus, and also Ghost, this wonderful algorithm from Aviva Zohar and Yonatan Sampolinsky that we adapted to a Vlad adapted to a proof of stake context. So then we can also go into a sharding, right? So sharding is this idea that instead of every node processing every chain, every node or every transaction, every node only processes a small portion of the transactions. And we do this by splitting the transactions up between a bunch of shard chains. In the ETH2 case, it starts off at 64 shard chains, and every node really needs to only process one shard chain. And these shard chains are kind of tightly coupled together through this beacon chain, and they all kind of talk to each other through the beacon chain, right? So here I have a diagram. If something happens over here where you see the letter A, then that gets linked into the beacon chain through this thing. This is a symbol for a crosslink. And then the next shard block in some other chain, shard B, kind of hash links to that beacon block. And so now through a kind of hash chain, B is aware of A. And so kind of receipts that get generated by A can be verified inside of B. So I often call sharding, or this kind of sharding, quadratic sharding. The reason basically is that, so in a regular chain, the capacity of the system is linear in the capacity of a node, basically because the capacity of a node just determines how many transactions you can process, right? So that's kind of O of n, or O of c, as I say, and then here it's O of c squared, right? So because the capacity of a computer determines two things. It determines both the number of shards that we can process, right? Because every node has to process the beacon chain, and the beacon chain has to keep track of all the shards. So the number of shards you can have is kind of bounded by the power of a node, but also the power of a node determines how large the blocks inside of the shard chains can be, right? So the load of the beacon chain is proportional to the number of shards. The load of a shard chain is proportional to the size of a shard. Both are proportional to the capacity of a node. And so the total number of transactions the thing can process is proportional to the capacity of a node squared. And my latest viewpoint is basically that quadratic sharding is probably all that we'll need going forward pretty much forever. Like you can totally multi-layer the scheme and expand it. And I actually talk about that in my scalability paper from 2015. You can do cubic sharding, exponential sharding, but I think like in practice, going beyond quadratic actually introduces more problems than it's worth. And that's one of the kind of research journeys that we made, right? The research journey basically being kind of starting off with a whole bunch of these wild ideas and designs, and then kind of really pushing them hard through this filter of basically pragmatism and simplification. So back to the history. 2018, ETH2 development started. June 2018, we did this pivot from trying to design ETH2 around the existing ETH1 chain to designing an independent beacon chain. March 2020, the Gasper paper. This is this paper for and Yan did a lot of great work along with a lot of other people, and Danny also kind of helped a lot with coordinating. Basically combining together a Vlad's LMT Ghost with my kind of Casper FFG, and trying to create this kind of holistic consensus mechanism. June, and since after that we wrote a whole bunch of specs. There was a lot of excitement about specs last year. June 2020, yay, phase 0 multi-client testnet. And August 2020, now phase 0 multi-client testnet that we market a little bit more heavily, right? So that's the Medalla testnet. Yay, Medalla testnet. I got a validator. Do you have a validator? There. That's the how do I point to do the like Uncle Sam wants you propaganda thing. There we go. You figure it out. So okay, a future of ETH2, right? So we kind of talked about the history. We can talk about the future as well. So first of all, and to reduce risks, the ETH2 deployment process is split into phases, right? So phase 0, which is proof of stake, phase 1, which is shard chains, but phase 1 only adds sharding for data. It does not add sharding for computation, which is an important distinction. Then after phase 1, we have phase 1.5, and phase 1.5 kind is what adds what we call the merge, which is basically where we kind of shut down the ETH1 chain, shut down the proof of work, and all of the ETH1 state, so balances, contracts, code, storage from the ETH1 chain is kind of moved onto ETH2 and users can transact on it. Phase 2, so sharding is not just data, but also adds computation, processes transactions. And then phase 3 plus, aka Ethereum 2.x, and of ongoing improvements to safety, efficiency, scalability, hopefully adding zero knowledge proofs to everything, though the basic structure of the ETH2 chain may well kind of never be changed again. This is contentious, so I know some people do want to kind of retain optionality to be more radical in the future, and there's other people that are in favor of kind of becoming more and more ossified over time, because ETH2 actually is sufficient for what we want to do with blockchains. So we'll see. I do think that realistically we're going to see more and more ossification over time, but the future is the future. So a long-term roadmap, this is this thing that I published on Twitter a few months ago, where basically talk about all of the different things that go into ETH2, right? So here's where we are today in phase 0 preparation. So multi-client test that we got that, client optimizations, we got a lot of that, can have a bit more of that, more audits happening as we speak, deposit contract, basically have that, then phase 0 launch. Then peer-to-peer networking, preparation for sharding. So a big difference between kind of existing networks and sharded networks is that in a sharded system, you have to also kind of shard the peer-to-peer. Like you can't just have a gossip system where everyone broadcasts messages to everyone. You have to kind of create systems that allow nodes to judicially download only a portion of the content. So in phase 0, we're kind of already using this for attestation to some extent, but in phase 1, this becomes kind of the backbone of the entire thing. Then implementation, audits, tests, ETH1. ETH1 is also very important, stateless clients. This is kind of the witness size bounding triad, as I've been recently calling it, gas repricing, changing to binary trees, code merkleization, making it possible to have a kind of smaller proofs that a block is valid, where that proof doesn't require you to have the entire state. Client optimizations, EIP 1559, this kind of economic fee market upgrade, a bunch of precompiles, ETH1 to ETH2 merge specification and implementation. So a bunch of things happening over here. And then here we have a kind of ETH 2.x, right? So single secret leader election, kind of basically a way of choosing block proposers that doesn't publicly expose as much information ahead of time, making a lot of progress on that recently, being more friendly to MPC validators, which would allow things like more secure staking pools, advanced cryptography, snarking and starking things, Casper CBC, lots of cool stuff. So challenges that remain, right? So first of all, testing is hard. We've done a lot of testing. We want to do more testing, but testing is hard. We know that from the experience that we had in ETH1 and in ETH2. We need to do a whole bunch of testing as well. Implementing phase one. Implementing phase one is something that's going to start very soon. As I mentioned, sharded peer-to-peer networking is one challenge. Aside from that, I think phase one is actually simpler than phase zero, so I'm hoping it's not going to be too bad. Merging ETH1 into ETH2. So this is a kind of combining together two separate different systems. It's that kind of, the crypto equivalent of space docking between where the shuttle and the space station are made by two different companies or even two different countries, right? So basically kind of taking these two kind of very intricate systems that are kind of mid-flight and kind of in this online procedure, just kind of combining them together and kind of, basically having a kind of one airplane fly into the other airplane's hangar. Okay, fine, I'm mixing metaphors. Economics of proof of stake contain unknowns. So how many people, how much ETH will participate, what are the pooling and centralization risks, economics of sharding contain unknowns, also a lot of centralization risks. But at the same time, every system has centralization risks, right? So like even proof of work has centralization risks. We have to kind of live with the ongoing fear that something will happen in the ASIC market that'll centralize the whole ecosystem and so on and so forth. But so I am confident that proof of stake is going to be better, but at the same time, we have to admit that proof of stake and sharding do both contain these unknowns. So there we go. Let's see. I've been told the countdown is 1 minute more than 1 minute ago, so I guess I'm done.